everybody. Today is the second lecture of Applied Physics. I'm Dr. Saad Ahmed, and today we'll be discussing about vectors, their properties, and how to use them for calculations. So let's start. Okay, a scalar quantity. So we'll be discussing about vectors and scalars. Let's describe these quantities. It, a scalar quantity can be described by a single number, and a vector quantity has both magnitude and the direction. Means that a scalar quantity can only have magnitude, while the vector quantity has both magnitude and the direction. A vector quantity is represented as this, a with an arrow on the top, and the magnitude can be written as this. Okay, so two vectors may be added graphically using either the parallelogram method or head to tail method. There are two methods of adding vectors. We are basically discussing vectors, and we can add two vectors by placing them head to tail. Means you can see here that a vector A is in this direction and vector B is in this direction. So vector C, the resultant, which is shown in blue here, will be C. Vector C is equals to vector A plus vector B. Adding them in the reverse order gives the same result. See, if you put B and then A, then the same result is again achieved, that is C is equals to B plus A. We can also add them by constructing a parallelogram. This is the parallelogram, this is A, this is B, and you just extend it in this direction, extend it in this direction, and the resultant shown in blue here will be again a same result. The sum of two parallel vectors A and B is this one. Sum of two anti-parallel vectors, one vector on this direction, the other on this direction. So you can see that it's A plus B, that one is deducted, the B is deducted from A, and you have this because the direction is opposite. Okay, all addition of vectors, all vectors must be drawn to scale and point in the proper direction. That is the important thing. If you see here that vector A has this direction, vector B has this direction, vector C has this direction, and D is in this opposite direction. So when you add them up and the result is shown with the dotted line, that is R vector, you get the proper addition, result of the addition. See, you can see on the left hand side the direction shown. Now you can visualize this properly and correctly. You can see that A is this one, B is this one, C is this one, and D is this one. And this is how it's working, and you are getting the result. Calculation using components. We can use the component of a vector to find its magnitude and direction using this formula. A is equals to root a square ax square plus ay square, and using this tangent theta is equals to ay upon ax. When we use the component of a vector to find the component of their sum, we use this for rx ax plus bx plus cx and so on, and for ry ay plus by plus cy and so on. Let's look at this example. Here we have two vectors A and B. R is the sum of vector, the resultant of A and B, and the component of R are the sum of the components of A and B, which means that A y plus by is ry and ax plus bx is rx. And if you draw and see the diagram, you can clearly observe that ax plus ay is this point, ax plus bx is this point, sorry, and ay plus by is this point. and if you extend it, you are going to get the same result which you use by simple addition method. So the component of R are the sum of the component of A and B. Okay, component of a vector. Adding vector graphically provide limited accuracy. This is very important because accuracy and precision is very important factor in scientific experimentations. So vector component provide a general method for adding vectors. Any vector can be represented by an x component ax and a y component ay. So we are going to use the trigonometry to find the component of a vector a x, which is a cos theta, and ay is a sin theta, where theta is the measure from the x-axis towards the y-axis. These are the simple mathematics and trigonometry formulas, and you must have heard and used these formulas before without knowing that what it does in actual physics and real life. Anyway, if we look at figure A, we have A and B components, sorry, A and AX and AY components of vector A, AX on the x-axis and BAY on the y-axis, and if you extend, as we discussed in the previous slide, you are going to get the result with the theta, the angle. And similarly for sine, AY is equals to A sine theta and AX is equals to A cos theta, and the resultant is here. Moving forward, these are some vectors and their directions: up, down, right and left. And coordinates are, you know these coordinates very well, that this one is plus plus, minus plus, minus minus, and plus minus. So these are coordinates, and by knowing the angle you can determine in which coordinate it is lying. Coordinate 1, coordinate 2, coordinate 3 and coordinate 4 as we use. Okay, the angles here, you can see the angles moving, that is from 0 to 90 is coordinate 1, 90 to 180 is coordinate 2, 182 to 270 is coordinate 3, and 271 to 360 is coordinate 4. And you must also know north, east, west and south. Understanding vector direction. To accurately draw a given vector, start at the second direction and move the given degree to the first direction. Start on the east origin and turns 30 to the north. North is this, you see, north of east, and 30 degrees. Sample, we have example here, and the direction of vector is 55 degrees north of east. The magnitude of vector is 2.3, which is here, which defines this, and measuring the same direction in different ways. If it is on the northwest, that is quadrant 2, it is 120 degrees. Quadrant 3, from the other side, it's minus 240 degrees. Northwest of west of north, 30 left to the y. This is 30 left to the y. This is because this is on the left hand side. North of west, this is north of west, or 60 degree above x. Again, basically this is the same thing which we are representing with different things. Anyway, vector notations. Rectangular coordinates, the dotted line shown in the red here are the rectangular coordinates. Polar coordinates, 14.1 meters at 315 degrees, 14.1 meters at 7 by 4 pi radians or 14.1 feet at 45 south of it. These are the same vector which we are describing with different. This is 315 degrees or 7 by 4 pi radian. You can calculate that on the calculator. So starting from this position, you can see that it goes all the way to this point, which is 315 degrees. Okay, and if you look at it from the other side, that is 45 degrees south of east. This is east and this is south, and this is south of east. Okay, vector components. Now we have vector components, x component, and this is y component. X component shown as dotted red line and y component as dotted y line. B vector, this is x component and this is y component. Remember, x component is on the x axis and y component is on the y axis. Here again we see the x component in the opposite direction and the y component in the downward direction. Okay, now the trigonometric functions. A right angle, you can see right angle here, and these are the labels. You can see A, B, and theta is the angle. C, sine theta is equals to P upon H, perpendicular upon hypotenuse. That is A here, the perpendicular, and H here, the hypotenuse. This is hypotenuse, this is perpendicular. Cos theta is base upon hypotenuse. Tangent theta is perpendicular upon base. I hope you are getting my point. Vector components. Look at this x and y axis. We have a vector A here with a theta degree angle. The x component is on the x axis, that is AX, and the y component is on the y axis, that is AY. This one and this one. So moving forward, AX is equals to cos A cos theta and AY is equals to A sine theta. On the other side, you can see the vector B is drawn in the opposite direction, and Bx and By are the x component, y components, and you can use the formulas here. You can see the formulas here. Bx is equals to B cos alpha and By is equals to B sine alpha. Okay, the sign of a x and y component depends on which coordinate vector lies. The sign of x and y component, right? So if it is in first coordinate, that is 0 to 90 degrees, we have discussed this, the positive x will and positive y values. If it is coordinate 2, that is 90 to 180 degrees, x will be negative, y will be positive. Third quadrant, 180 to 270, negative x with negative y, and the fourth coordinate, that is 270 to 360 degrees, positive x and positive y value. I told you before, first coordinate is plus plus. Plus plus means x is plus and y is plus. Second coordinate is minus plus, that is x is negative, y is positive. Third is minus minus, and both the values x and y components are negative. And fourth is plus minus, that is positive x with a negative y. So just try to remember this in a sequence and you will be able to get it. Vector components continuing. So we can see here that AX is equals to A cos theta and AY is equals to A sine theta, because x component is cos and y component is sine here. So what are the x and y component of vector 40 meters at 60 degree? Let's see. Ax is equal to 40 meter cos 60, y is equals to 40 meters sine 60. You are going to get two values by solving this, that is 20 meters and 34.6 meters. What are the x and y component of 60 meters per second at 245? So 60 meter per second multiplied by cos 245, 60 meter per second sine 45. Using the calculator you get these answers, that is 25.4 meter per second and 54.4 meter per second. Adding and subtracting vectors using component. Add the following three vectors using component. These are the three vectors. First vector, I hope you are getting the point, the basic concept. Now we have a vector with the magnitude and the direction. Vector A has 30 meters, that is magnitude, and 45 degree is the direction. The vector A, then vector B here is 50 meters and 0 is the direction because it is lying straight on what? X-axis, right? And the vector C is 30 meters and 90 degree, and you can see this is 90 degree and 30 meter is the magnitude. So resolve each into x and y component. First step is to resolve them, and we know how to resolve them by using the formulas discussed earlier. That is Vy is equals to V sine theta and Vx is equals to V cos theta. Okay, we can see that adding and subtracting vectors using components, we have found out the components, that is Ax and Ay, and these are the values we are getting. Bx and By, these are the values, and Cx and Cy, these are the values, right? Next, add the x component of each vector and add the y component of each. We remember we had three vectors and we are going to add the x's x components and the y components. So adding the x component, that is summation x, we get this 71.2 because it was 21.2 plus 50 plus 0, and y components are 21.2 plus 0 plus 30, that makes 51.2. So we have added the components of each vector. Construct a new right triangle using summation x as the base and summation y as the opposite sides. So let's do it. This is summation x, the magnitude is 71.2 and the direction is on the right side. This C summation x y, that is 51.2 and 90 degree. This is the hypotenuse, is the resultant vector shown here in the red. Now finally use the Pythagoras theorem to the length, that is the magnitude of the resultant vector, and we can see that you know that the formula is root ax square plus ay square, and the resultant is 87.7, that is the magnitude. And let's find the direction using the inverse tangent formula we discussed earlier. Angle here is tangent inverse 51.2 divided by 71.2, and the angle is 35.7, and the quadrant is 1, and you know that quadrant 1, if you extend it like this, you can see that it is positive and quadrant 1 here, right? So the resultant is 87.7 meters at 35.7 degrees. Use the calculator to calculate this. You do it quickly so that you are basically confirming it for yourself. Subtracting vectors using component. Again, same three vectors. What we are going to do is subtract A from B and then add C, and the resultant will be, we call it R. Okay, this is the pattern A plus, we put a bracket here to isolate minus B and plus C. Vector at 30 meters at 45 degrees, vector B which is minus 50 meters at 180 degrees, and vector C 30 meters at 90 degrees. Resolve, again the same steps we are going to follow. Resolve each component into x and y components, resolve each into x and y component, and we get this, which you remember we have seen this before. x, ax, ay, bx, by, and cx, cy. For three vectors, you have calculated the values using the formula, and now add the x component to each vector and the y component of each vector. We added summation x and summation y. We get 28.8, that is in negative, and plus 51.2 in positive. Construct a new right triangle using the summation x and summation as base and summation y as the opposite sides. So simple. This is x-axis. Because it was in negative direction, that is why we are going from right to left. And then what we are doing is going opposite side, that is upward here, for the positive and 51.2. The hypotenuse is the resultant vector, but the direction is different now. And using the Pythagoras theorem, find the magnitude of the resultant vector. We have values of x and y. We use the Pythagoras theorem formula, put the values in, 51.2 squared, 28.8 squared, then you get to add them up, and root value of square root is, now the resultant is 58.7. Find the angle using inverse tangent of the opposite side over the adjacent side. See, the angle tangent inverse is 51.2 upon minus 28.8. The angle comes out to be minus 60.6 degrees, and you subtract it from 180, gives you 119.4, and you can see here that it is the second coordinate, and the resultant is 58.7 meters at 119.4 degrees. Okay, the unit vectors. A unit vector has a magnitude of 1 with no units. The unit vector I points in the direction plus x points in the y direction, and k points in the z direction. See this diagram. You have three axes, I, j, and k. J on the y-axis, I on the x-axis, and k on the z-axis. Any vector can be expressed in terms of its component, that is a xi plus ayj plus azk. Okay, the unit vector I and j points in the direction of x and y axis and have a magnitude of 1. See this. We can express a vector A in the terms of its component. We know that, we have done this before. So this is the value. Scalar product. The scalar product, also the dot product, it's also called the dot product of the two vectors, is AB cos theta. You are basically multiplying it, and you can see that these are the two vectors in figure A. Place the vectors tail to tail. You are using tail to tail here, not head to tail, it's tail to tail for multiplication, the dot product. Then what you do is you find the magnitude times the component of B in the direction of A. This is the thing, B cos theta. Then what you do is A dot B also equals A B bracket A cos theta. See this? The other way around, it is like this in the second diagram. Another example, if theta is between 0 and 90, A and B is positive. If theta is between 90 and 180, then dot product is negative. If it is 0, then dot product is direction of A. In terms of component, A dot B is equals to AX BX plus B AY BY plus V AZ BZ. Examples show how to calculate scalar products in two ways. Let's see. We have A vector and B vector, both in different directions. You can get the components of it, and you check the angle. This is I, this is J, and this is I on x-axis and J on y-axis. From I it is 53 degrees, and this one is 130 degrees, and the difference is 53 minus 130, you get this theta. The vector product, cross product of the two vectors has magnitude, and use the right hand rule to find the direction of A cross B. Before it we was discussing about the scalar product, that is the dot product. Now we are discussing about the vector product, the right hand rule. We have again two vectors A and B, you can see here, and the direction will be placed A and B tail to tail. You have to put your place fingers of the right hand along A with a palm facing B. Curl fingers towards B. You can hang on to this B vector as shown in the figure, and thumb points in the direction of A and B. This is the right hand rule. These are simple 4 steps. B in B and A is equals to minus A and B. The vector product is anti-commutative. See here, the direction becomes opposite. The magnitude A and B equals AB sine theta. See, this is vector B, this is vector A, and you have this B sine theta. So the magnitude of A times component of B perpendicular to A, and the magnitude of A into B also equals B sine A. Here it was AB sine theta, and here it's BA sine theta. So simply what you are going to do is put the vectors tail to tail and calculate this from this point A sine theta. Use AB sine theta to find the magnitude and the right hand rule to find the direction. I want you to take the snap of it and try to solve it on your copy. So that is it for today. If you have any questions, you can ask me by contacting me, and I hope you will be able to solve this problem and get the results, and hope to see you again soon with the third lecture. Thank you very much, and Allah Hafiz.